So you might remember when we were just starting the course, we talked about binary events. And by binary events, I mean the events which either happen or not. So anything that you can answer in yes or no is a binary event. The most popular example is, again, the coin toss, because the coin has only two faces. So you might ask something like, was it heads? And it's either yes if it was indeed heads, or no if it's tails. Sometimes you can turn any other kinds of events into binary events too. So when you are throwing a die, you have 6 faces it could show up, right? So you have 1, you have 2, well, and all the way up to 6. So you might be used to regard this as an event with 6 different outcomes. But we can do something like this. We can say, hey, was it more than 5? So usually in tabletop games which have mechanics defined by dice, they use this notation. So 5 plus means either 5 or more. So you can say, you can regard the die as a binary event which either gives you 5 plus, which is 5 or 6, or less than 5. So 1, 2, 3, and 4. So what we are doing, in fact, is we are grouping those 6 outcomes into 2 groups and regarding those 2 groups as 2 outcomes that we are interested in. Well, but anyway, so say you have an event with 2 outcomes. We call such events binary events because 2 outcomes, you see. So the binary event is an event with 2 outcomes. And I want to now focus on special kinds of binary events. So I want them to be binary and independent. So if you repeat the event, the outcome after your first try does not in any way affect the outcome of your next one. Excuse me. So I want binary events which are independent. And which have the same frequency, the same probability. So for example, if my first event has probabilities of 40 and 60%, just as an example, then I want my second event and third event and fourth event and so on also be 40 and 60%. So the easiest way to achieve that is repeating the same event, right? And those repetitions of events we will call trials. That's the tradition. We used to use that word, trials, for repetitions of an event. Okay, so I want a binary event, a series of binary events, so several trials, which are independent of each other. And as I already said, the easiest example will be a coin toss, where we have heads and tails, and let's for now stick to the fair coin. So probabilities for both outcomes are 0.5, 50%. We need to choose one outcome as favorable. I will choose heads, so I will denote probability of heads as P and probability of tails as Q. Okay, so now let's make 3 coin tosses. In statistics, we formulate it in a slightly different way because you know we are scientists and we like the words that sound clever and so on. Just kidding, that's not the true reason, but anyway, so let's make 3 coin tosses. Translates to let's perform an experiment with 3 trials. So anyway, so we are tossing 3 coins, and we can have different outcomes, right? So we can have something like heads, 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 or we can have heads, heads, and tails, or heads, tail, and heads, and so on and so forth. Tail and 2 heads, or maybe tail, tail, and head, or tail, head, tail, and also head, tail, tail, or 3 heads. 3 tails. So, if you look at that, each of these outcomes is a random event. So we have a random variable which can be either heads or tails and so on, but we can introduce a new random variable. So let me count the number of heads in different outcomes. So here I have 3 heads, 2 heads, 2 heads, 2 heads, and for all 3 of these I have only 1 head, and here I have 0 heads. So in a way we have a new random variable which is a number of favorable outcomes in our trials, in our experiments. So let's see what's going on with that variable. I'll create a frequency distribution. So 0, 1, 2, and 3. And we see that we have only one case with 0 heads. And we have 3 cases with 1 head. 3 with 2 heads, and only 1 with 3 heads. So these are our frequencies. We can translate that to probabilities, and for that we will just divide everything by the total number of outcomes, which is 8 in this case. So 1 over 8, which is 0.125, 3 over 8, which is 0.375, and the same here, and the same as the first one here. Okay, so now we have our frequency table for that binary event, and it was easy. We were able to list all the outcomes and and just count them. But that will not always be the case. So for now, let's just finish this part. I will put a chart here, a graph. So 0, 1, 2, and 3. Let this be 1/8, and this one 3/8. So I have 1/8 for 0, I have 3/8 for 1, the same for 2, and again 1/8 for, yeah, I misplaced my 3, it should be here, for 3. So this here is my graph. We can turn it into a bar graph or column graph, whatever you call it. It won't change the meaning. So here it is. You might notice that it's symmetric. Left and right sides are similar. So let's try something a little bit different. The same setup, however this time my coin is not fair. So I have one side come up with larger probability. So maybe our heads have probability of 75% and tails have a probability of 25%. So what happens in this case? Well, again, if we toss 3 coins, we will have the same outcomes. So for example, the one with 0 heads, which is just 3 tails, or with 1 head, which is this one, or this one, or this one, and we can go on like that. But for now, so let's see what are the probabilities. I can't just count the outcomes here now, because different outcomes have different probabilities. So in this case, probability for this and for this were the same, because all the both heads and tails have the same outcome. But now here it's different. So probability for this, for example, is 0.25 cube. Well, in fact, this is 1/4 and this is 3/4, and let's write it here somewhere. So P is 3/4 and Q is 1/4. So here we will have 1/4 times 1/4 times 1/4. That will give us 1/64, or Q cube. Here I have 3/4 for heads, and then 1/4 for tails, and then again 1/4 for tails, and that's 3/64, which is P times Q squared. And then if I calculate for this, I will have the same, just the same number as here, because you see they have the same number of heads and tails, just the order is different. And when you are multiplying numbers, the order does not matter. So we will again get 3/64, which is P times Q squared, and then we will have the same for this one. So probably you already know what will happen if we move to two heads. So either this or this or this. We will have two 3/4s and only one 1/4. So it will be 9/64, which is p squared times q. And the same for next two. And when you have three heads, it's just 3/4 times 3/4 times 3/4. It's 27/64. And that's of course p cube. So we found the probabilities for each separate outcome. However, what we are interested in is probabilities for these numbers: 0 heads, 1 head, 2 head, 3 heads. And I can see that I have only one case where I have 0 heads. And probability of that case is 1/64 or q cubed. And then I have 3 cases for 1 head, and each of those 3 cases has the probability of pq squared. So overall probability for 1 head will be 3pq squared, or let me check, was it 3? Yes. So then 9/64. And for the next one we have 3 cases, and each of those 3 cases has the probability of p squared q. So overall probability is 3p squared q, and it's 27/64, I guess. Yeah. And for the last one we just have one outcome with the probability of p cubed, which is again 27/64. So that's it. And you might have noticed something familiar in here. So looking at this, we already know this thing. We have seen that thing. So if we add those things up, we will get the special product p plus q cube, which is p cube 3p squared q 3p q squared and q cube, right? And each term in here is the probability for this. And we know that this formula is the binomial formula. Well, in fact, that's the one particular case of binomial formula for third power. And in general, it looks like p plus q or a plus b or x plus y, whatever you are used to the power n. So this is the case when n equals 3. And here's our probability. So for binary event, experiment with 3 trials, you just take the terms of binomial formula for n equals to 3 with third power. And I can suppose that that must mean that for 4 trials it should be n equals 4, and for 17 trials it will be the same formula with n equals 17, and so on. So our probabilities comply to the binomial formula, and that's the reason for the name binomial distribution. So this is one particular distribution, and it's called binomial distribution just because it's probabilities or relative frequencies comply to the binomial formula. Okay, so let's put up the graph here again. Most probably it will not be to the scale, because I'm not going to make exact measurements. Well, maybe let this be 3, then this will be 1, and then this one is 9, and here we'll have 27. Okay, so scale is more or less okay now. And for 0 we have 1 over 64. For 1 we have 9 over 64. I'm making a bar graph here because the dots might be harder to see. And for 2 and 3 we have 27 over 64. So like this. And one thing you might notice is that the graph is not symmetric anymore. It's skewed, and it's highly skewed. And that's because our P and Q are not equal anymore. They are different. It's not 50-50. And the closer they are to each other, less skewed our graph will become. The further apart P and Q are from other, the more skewed the graph will be. And in the ideal case where P and Q are just equal, so 50-50, we will have this symmetric graph. Okay, so that's our binomial distribution. But what about the other cases? What if we don't want to make 3 trials? Maybe we want 17 trials. How do we find these expressions? Well, you just use the binomial formula. And the binomial formula tells you that each term is C k out of n p to the power k q to the power n minus k. So C is just number of combinations. Okay, so we know that these are the terms of binomial formula. What about the probabilities? Well, we also know that each term is the probability for corresponding value of k. So if you have some random variable which has the binomial distribution with n trials and probability p, then you will have, so for example, x equals 0, you will have c 0 out of 10, p power 0, q power n, which is of course just qn. For 1, you will have c1 out of n, p1, qn minus 1. This thing is just n, qn minus 1. For 2, you will have c2 out of n, p squared, qn minus 2, and so on and so forth until you reach n. Okay, so we have the formula now. for probabilities. So let me put it here. P for x equals k is just number of combinations of k out of n, p to the n and q to the n minus k. So yes, p to the k and q to the n minus k. And here n is number of trials. And this formula will work always. It doesn't matter if your P and Q are 50-50 or if they are different. But the only thing is that you should have only two outcomes. So there's nothing except P and Q. And that means that P plus Q is 1, right? 100% that either one of those happens. Okay. So if you want to, for example, look at the binomial distribution of experiments with 4 trials, you will just substitute 4 for n, and you will calculate your probabilities for each k. Let me just show you an example. So, what can we take? On the lesson we had that example with sewing machines, that one way. I want something different. Well, let's say you are buying a new tires for your car, and usually you buy them in batches, so you buy 4 for all wheels, or maybe even 5, because you also have the replacement wheel. So you go and ask sellers how many of those tires come maybe flat or maybe pierced from the factory. So something happened, the machine that was producing those tiles did not work as intended, and because of that some tiles come with defects, and you want to know what's the percentage of those defective tires. And sellers tell you, well, real sellers will tell you, yeah, brother, these are 100% good, there's never any defects, and so on, because they want you to buy the tire. But the clever seller, the smart seller, will say you something like, well, out of each 100 tires, 2 were defective. So you might then suppose that probability for a tire having a defect is 2 over 100, so 0.02 or 2%. Okay, so now you have everything you need. So you can find your Q, and it will be 0.98. What's the probability that there will be absolutely no flat tires, defect tires, or that there will be 1 or 2 or 3 and so on? So we just use the formula. I'll write that formula one time. 0 out of 5 P. So K is equal to 0, so P to the 0, Q to the 5. Okay, one more time. C 1 out of 5, P power 1, Q power 5 minus 1, 4, and so on. And we can calculate those probabilities. So you already know how to find the number of combinations. You can look it up in our previous videos, or you can just Google it, or take it from the book, whatever you like more. So here, for our first case, for 0 it will be 1, and for 1 it will be 5. So let me put that 5 here, and this, I won't write the 1. P power 0 will be also 1, so we are left with only q, which is 0.98 to the 5th power. Okay, so it's 0.90 approximately. Excuse me. Okay, so here we have 0.02 times 0.98 power 4. So this here is 0.9. Again, approximately, of course, I'm rounding up. And here we will have C2 out of 5. So that will be 5 times 4 divided by 2, I guess, 10. So we will have 10 times 0.02 square, 0.98 cube. Okay, and that's 0.004. Well, you can imagine that if we go on, if we calculate for 3, 4, and 5, we will get even smaller numbers. So, there is a 99% probability that you will have either no defects or only one defect. To have 2 of your newly bought tires be defective, you have to be extremely unlucky. So, if you have exactly 2 defective tires, probability of that is 0.4%. And it's even smaller for 2 and 3 tiles. Oh, sorry, for 3 and 4 tiles, or 5 tires, and so on. So that's one way of, one example of application of binomial distribution. Okay, now, so we know that for each x that's equal to k, you have a probability of c, k out of n, p, k, q, n minus k, right? And I want to calculate the mean value. So what will be the mean value? And we will use previous result that we get in previous video. So I will sum up, I will take each value of x, so I will take different values of k, and I will multiply them by the probability for that value of k. And then I'll sum up. So I'll have k times c k out of n, pk, q, n minus k. And I will have to sum over all the values of k. I'll make one more step. So what does that mean? We substitute 1 for k. So 1 times c 1 out of n. Sorry. We should start with 0. Okay, but 0 times anything is 0, so I'll just put 0 plus 1 c1 out of n, p to 1, q to n minus 1, and then 2 times c2 out of n, p to 2, q n minus 2, and so on, until you reach the end, which is n times c n out of n, p to the n, and q to the 0. Okay. So if we sum it up, we will get our mean value. And now, that's the homework for you. So, start with this thing where k ranges from 0 to n, c k out of n, p k, q n minus k. You have to perform all the intermediate steps, and in the end you will get your result, and it will just be n times p. That's a tedious task. It takes much time. It might be boring to some of you, interesting to others. It depends on a person. Somebody that finds it be boring, somebody just the opposite. And it's not mandatory. So, well, it is mandatory, but only for the ones who want to strive for the perfect final grade. So if you are content with something like 95 or 98 even, then, oh sorry, not 98 of course. So if your aim is anything higher than 95 as a total grade for the term, you will have to do this. There is no excuses. If 95, 90, 87, something like that is just alright for you, then you can just ignore this task. There will be maybe 2 other tasks which go into the same place, which are mandatory for the perfect grade. But okay, so this one is your homework, and I will focus on this. So if I have some random value which has the binomial distribution with n trials, probability of success being p, then my mean value will be just n times p, and my variance will just be n times p times q. So going back to our example with fair coin, is it this one? No, it is this one. Oh no, again no. Here it is. So n is 3, p is 0.5, so my mean value should be 3 times 0.5, and that's just 1.5. And if we look at the graph, it's right here in the center. And for the symmetric distributions, mean is usually in the center. So it looks good. Our variance here is another 0.5, so it will be 0.75. So that's our variance. If we move to the unfair coin, to asymmetric case, then so our n is still 3, but p is 0.75 now. So my mean value, I'll put it here, is 3 times 0.75, and it's just okay, 2.1, 2.25, 225. So it's somewhere here, closer to 2 than to 3. Yeah, seems legit, looks alright. And the variance, okay, over 4, 0.55, 0.56, so approximately 0.56. And you can use that everywhere. Again, if you have binomial distribution, then here are your formulas. Just like in this example with tires, you might be interested in the mean number of defect tires. So you just take your n, which is 5, and multiply by p, which is 0.02. And you'll get 0.1. Yeah, so that means, well, for 5 tires it will be meaningless, but it means that if you buy 5 tires, bunches of 5 tires, 5 times, so 25 tires in total, then one of them will be defective on average. Okay, so that's the binomial distribution for you. We will have continuous distributions, which are more complex and which need either specialized pre-made tables or using the calculus to process to be able to calculate anything. And sometimes you won't be able to, maybe you don't have those tables, or maybe you want to calculate it by yourself and you are okay with calculus, but you got some of those nasty non-analytical integrals or something like that. So in all those cases you will work with approximations, and we will see when we move to continuous distributions, we will see that some of them, the important ones, can be approximated by binomial distribution. But that's all for now. So thanks, bye, see you.